Hello, good day. Welcome to lecture 9. In the previous lectures and discussions, we've been looking at moments of inertia and mass moments of inertia. So in this case, we are now advancing into the mass product of inertia, principal axis and irregular objects. Right, so in this discussion is basically shifting from the area regime into the mass regime. So for our discussion, we will start with the definition of mass products of inertia. Remember, we worked on area products of inertia, so we actually know the area product of inertia, but the mass product is something that we had not yet calculated. Then principal axis, we did this, and we did this in 2 steps. We first of all used a normal circle, right? So that circle was through a transformation of the normal axis into some other system of axes, which has the product of inertia as the vertical axis and the moment of inertia as the horizontal axis. This was further developed by Moore's circle, so basically we had to do some conversions there. Now we are looking at principal axis for the mass moments, and then bodies of arbitrary shape. Basically these are bodies that have any other shape that is not geometrically easily defined. Right, so for us to get started, we will define the mass product of inertia. The mass product of inertia is basically derived from the moment of inertia of some body, of some mass m, about an axis that is not either the xy or the z original axis. So it's about some other axis. In this case, the axis that we are concerned with is this axis, which is the OL axis. The OL axis is what we will use to actually develop and come up with the mass product of inertia. So as you can see, we have the XYZ axis on which we have some OL axis that is starting from the origin O. This axis points in a direction lambda, and the mass element is therefore located at some vector r from the origin. The angle between the direction of the vector and the axis is theta, and then we can use some p there to relate our r and our lambda. So if you use this p, which is actually a perpendicular distance from the mass element to that axis, then your mass moment of inertia becomes the same as we had, which was r squared dm. In this case, we'll just use p squared, just because we're using our r elsewhere. So basically, our mass moment of inertia is defined as the integral of p squared dm. Now, we can actually relate our p squared, or we can write our p squared in terms of some terms that are in lambda and r. Lambda is our directional vector, but we can tell from this setup that the product, the vector product lambda cross r, it's actually equal to the magnitude of lambda multiplied by the magnitude of r, right, multiplied by sine theta, the angle between them. We know that the magnitude of a unit vector is 1, and then that would be just r sine theta. At the same time, if you look at the geometry of this triangle, let's name it OAB. The geometry of triangle OAB allows us to find the trig ratio of the sine of that angle theta being equal to what? The opposite side, P over R. So therefore, our P becomes equal to R sine theta. If you look at this expression and what we've done here, it is therefore possible for us to simply define our lambda cross r, the magnitude, as simply equal to this r sine theta, because the magnitude of lambda is 1, and therefore it's equal to p. Now, if you integrate that p squared with respect to m, it simply is the same as integrating the square of this cross product magnitude. So that is why we have that equation, which is called equation what? Okay, there's no, okay, 943. Right, so that's equation 943. It stems from this definition of P. Now, let's look at the vector product values that we have and actually find the magnitude. Remember, there are many ways to find the magnitude of a vector. So we use the magnitude equation, but we can also find the actual coefficients of the I, j, and k components, and then those coefficients we can square them using that. If you still remember, we can find, let's say, a resultant is equal to now the resultant in the x squared plus the resultant in the y squared plus the resultant in the z squared. So by the same principle, I think you should be able to remember that your lambda cross r can simply be found by, so if we say lambda cross r, this is the same as the determinant of the matrix I, j, k, in which our lambda x is the x component, lambda y, and our lambda z. And then our r is simply an x in the I plus an I, a y in the j plus a z in the k. So therefore we have an x, y, z there. Right, so from what we have now, we now have a matrix whose product, whose vector product we can actually find in terms of its terms. So let me just continue this calculation somewhere down here and write our lambda cross r to now be equal to, let's look at the I, coefficients of the I. So the I will have a z lambda y minus y lambda z in the I, and then plus the j will have a x lambda z minus z lambda x in the what? In the j. And then you can continue for the k. So if then we want to find the magnitude of this vector, obvious, we just square that term because that is the lambda in the x. And then we also square that term, that is the lambda in the y. For that reason, we have the following result from equation 243. We have the first term, for example, here, lambda x y minus lambda y z. So that's for the k term. Our x term, which we have done, is our z lambda y minus y lambda z. So this is z lambda y minus y lambda z. Then it's squared, and then the last term, we said x lambda z minus z lambda x. So x lambda z minus z lambda x. So which means this is the only term that we had not yet found out. So you can do your math and actually find the term for the k, which should be this one. Right, so basically now we now have an expression. We now have a convenient expression. What are we trying to do? We want to derive the mass product of inertia. From what? From the moment, mass moment of inertia about some axis that is not the x, y, or z axis. Now, if we algebraically expand that bracket, obviously, let's say for this first term, the first term will just become a lambda x in this lambda x squared, y squared. Remember, we're squaring the whole bracket. So obviously, this will be minus lambda x, lambda y, x, y, plus lambda y squared, x squared. That's just the expansion of the first bracket. If you do the same and do the same, you will come up with the solution that is shown in equation 9.44. This solution shows you, that there is a term, for example, this lambda x multiplied by y was squared, isn't it? This lambda x multiplied by z was also squared. For that reason, you've got your y squared plus z squared in that bracket, and your lambda x squared is on the coefficient side because it's a constant. Remember, your lambda is simply a what? A directional cosine. Then the same applies. You would find that part and that part. As far as the terms that are, okay, this must be minus 2, excuse me. So as far as the terms that are being cross multiplied there, we have this 2 lambda x lambda y multiplied by xy. 2 lambda x lambda y multiplied by the integral of xy. Why? Because it was in the integral sign. So the same applies for the rest of the terms. You would find these cross multiply terms. In the end, what you have is equation 9.44. So please follow the algebra so that you can actually tell, okay, so this equation literally comes from this step, right? Then when you have this equation, there are some interesting things in that equation. There is this term here. Do you still remember this term from yesterday's lecture? This term is simply your what? Your moment of inertia, mass moment of inertia about the what? About the x-axis. The same applies. Mass moment of inertia about the y-axis. Mass moment of inertia about the z-axis. These are the terms that you see at the top there. Do you still remember this term? This is now your product, mass product of inertia. And it looks exactly the same like what we had for the areas, save that we are replacing the area with the mass. Right, so I think you already know how you can actually do that conversion. So happy days. So therefore, from this equation come the definitions of the mass product of inertia. So the mass product of inertia about the xy is the integral of xy dm. Likewise, about the zy is the integral of yz dm, and so on and so forth. So therefore, in terms of the ixy, ixz, iyz terms, our equation for the moment of inertia, mass moment about that OL axis, the equation for that mass moment, it can now be rewritten in such a way that we replace this term with an ix. So therefore, lambda squared is now having a coefficient ix. Lambda y squared now has a coefficient iy. There we have it. And so on and so forth. Our products now appear in these cross-multiply terms. Hence, the definition of the product of inertia. So therefore, the product of inertia is actually obtained, the mass product of inertia, that is. It's obtained from a determination of the mass moment of inertia about some arbitrary axis. Now, therefrom, this means that we can actually apply the mass product of inertia in the parallel axis theorem. So equation 9.47 there is basically showing us the parallel axis theorem, the mass product of inertia, just like we saw for the area product of inertia. It also obeys the parallel axis theorem. So therefore, for you to find the mass product of inertia ixy, all you need is the centroidal product of inertia ix, x prime, y prime are the centroidal axes, plus the mass multiplied by the product of the centroidal coordinates. This means that we now have all we need for us to find mass product of inertia. Let's see what that means through an example. Example 9, okay, so it's a question problem 9.149. Determine the mass product of inertia ixy, iyz, izx of the steel fixture shown. Then I'm given the density of steel. Okay, so we have some density rho given there, and then we've got the steel fixture shown. For us to get, for example, the first one would be ixy. We will need, right, okay, so this shape, as you can see, this shape is a mix of many shapes, right? For life to be easier, you have to demarcate it into different shapes. So let's demarcate it, let's subdivide it. This can be shape number 1, so it ends there, right? So this can be shape number 1. Shape number 1, it also it's made of, it's a volume, isn't it? So it's made of the other side as well. So for that object number 1, we can give some names of these variables. We can give this side to be what? To be A, then this side is a B, this side is a C. So we now have the actual volume, we can actually find it, right? Then the second object is the middle object. So as far as this dividing is concerned, it's purely up to you, right? Whatever you find easier, you can apply. So for the second one, it would have dimensions what? It has a length A, it has a width, okay, so we now need more dimensions. So let's just call, okay, let me just give names to all these dimensions. So let's call this one D, since I had ended on D, so that this becomes a what? This becomes an E, this becomes an F, right? This becomes an F. This becomes a G. We know G, according to that, is equal to 40 millimeters. We know that F is equal to, this is our F, isn't it? Yes, F is equal to 70 millimeters. Right, our E, what is our E equal to? Our E is, okay, we can just have this total B, isn't it? We can just have B minus D. So we have the total, we have the actual E. Then what next? We've got some radius here, R, and then what else? I think we're good. I think we're good, isn't it? Yeah, I think we're good. Right, so we've just given some names to those variables. So we will now be happy to write our Ix for element number 1 or object number 1. Then we need to also define this other object. We said this is now object number 3. Then this other one can be our object number 4, because we have some object there that was removed. So in actual fact, when we're calculating, we'll remove this mass product of inertia due to that semicircular region. So Ix y of 1 plus Ixy of 2 plus Ixy of 3 minus, remember, the 4 is void. So we are removing Ixy of element number 4. Now, what is our Ixy of element number 1? Our equation for the mass product of inertia tells us that we only need to find the centroidal mass product of inertia, add it to the product M1 X bar of 1, Y bar of 1, and then we're good. What is the mass product? What is the centroidal mass product of inertia? If you just look at this, we want it about the what? The xy. Do you notice that about the x, we've got some symmetry, about the y, we've got some symmetry. So which means our mass product of inertia, which is the centroidal one, it simply becomes 0. Plus, what is our mass? What is M1? Okay, so if you are given some density, this means that you can actually find your mass as density multiplied by the volume, isn't it? Where your volume is just an area multiplied by some other side or thickness. So our density is rho. What is the volume of a rectangular prism? Isn't it? Our element number 1 is a rectangular prism. So it's simply A multiplied by B multiplied by C, right? So that's an ABC, A, B, C. Then we multiply this by what? Then we multiply this by what? We are multiplying this by X bar, Y bar. Our X bar is just half of that A, and then our Y bar is just half of that B. So we are happy with the first part. How about Ixy of 2? Ixy of 2. Right, we won't rewrite the equation, but what we know is that it is also symmetric about at least one of the axes, so which means this is a 0 plus our rho multiplied by the volume of that second object. Second object, the volume is just A, right? A times F times E, AFE. So rho times AFE, AFE, yes. We're done. What else? What is X bar? X bar is still half of A. What is Y bar? It's now half of E, right? So it's times half of E. Right, so we've got Ixy of region 2. How about region 3, object 3? Okay, it's another it's another rectangular prism. So we can see symmetry there, plus rho multiplied by what? Obviously A multiplied by B multiplied by G, ABG, ABG, ABG. What is its X centroidal? It's still half of A. What is its y centroidal, it's half of b. Right, what about the last one, the IXY of region 4? IXY of region 4. Region 4, does it have some symmetry? Yes, we see it has some symmetry. So that would be O0 plus rho multiplied by its volume. What is its volume? This is half of a what? Half of a disk, isn't it? Half of a disk with some thickness, right? Or half of a cylinder. Let's put it as half of a cylinder. So that's half of a cylinder has a cross-sectional area, which is just pi r squared. We are already using that r. So it's half of pi r squared, then multiplied by its thickness. Its thickness is g. If you can see it, that's its thickness there. So that is the same as this g. We now have the mass, isn't it? Rho times the volume. Then x bar. What is x bar? Obviously, x bar is half of a. What about y bar? Our y bar, okay. Our centroid is somewhere there, isn't it? In this vertical axis. Our centroid is somewhere there. So if our centroid is somewhere there, we need to measure the centroid from this part. So let's just see if we can find the centroid from the top of this circle. This is where we need to use some tables. Let's call some tables into the picture. Okay, where can we find the centroid of a semicircular area? So we can use the data sheet on figure 5.8a. So that data sheet simply tells you that for a semicircular area, please always be careful, because the semicircular area is looking almost the same as the semi-elliptical area, right? So be very careful with these. So there we have our semicircular area. Its centroid is actually being measured from the base, or the flat part, right? So that we can quickly identify that. We can tell that whatever we will get from the book is in between this and that. That is the centroid that the book will give us. So whatever we will do, we are going to find this y bar in our setup, right? Our y bar of 3 is going to be what? We can actually do some math and we can say whatever is the height there minus whatever is defined here, right? And we know the height is b, isn't it? So it's actually b minus whatever the centroid is defined as in what we will check just now. So the centroid in this case is being defined at a point y bar, and that y bar, according to this part, is actually, so basically what I'm pointing at is this y bar here. So what we are looking for is the y bar, and we can see that for the semicircular area, we find it as 4r over 3 pi. Our r is simply this radius of this semicircle. 4r over 3 pi, that's what we would use. 4r over 3 pi. Happy? I think we're happy. So this implies then that our IXY must simply be equal to the sum of all those. Right, so since we already have these equations, I think you can actually use some program. You can use some program to, not a program as such, you can use a calculator that can store variables. Yeah, it is not programming. So let me just be clear about that. So I've got a Python somewhere here. I think I can, Python is free, by the way. So for you programmers, I think engineers, I think you will use these pieces of software a lot. So Python is free. So what I'll do is I'll just call it and recall that what we want to use are some mathematical functions. So that's what we want to use. So we now have all our mathematical functions loaded. We've got a module there. So we are good to go, right? So let's now just have fun and just put in all these things, isn't it? Let's just put in all these dimensions. Then we can actually do algebraic math on this program. Okay, so let's run it. Let's run it. So what we have is our A. What is A equal to? Our A is equal to the dimension 80 millimeters. In fact, let's define the millimeter first. So that's the good part about using these programs. Just define the millimeter. You know that is just 1 multiplied by 10 raised to the what? The minus 3. So your E for Python is just that. So that's the millimeter defined, so which means our A is basically now going to be equal to our A is 80 millimeters, so that's 80 millimeters. So we're multiplying by the millimeter, so we're good for the A. What is B? B, by the same sign, is equal to 50 millimeters. 50 millimeters. Actually, I can copy this since I'm using it a lot, right? Right, what is our C? Our C is 50 millimeters, so it's the same as B. No need to do too much. What is our D? D is 38 millimeters, so it's 38 millimeters. What then is our E? Our E is reserved, right? So E is a natural number, so I will not use that constant. I'll just say side E or ES. So side E is equal to, from our equation, our E is simply a B minus D, and E is simply a B minus D. So there we have it. B subtract D. Then the next is what? An F. An F is defined as 70 millimeters. 70 millimeters. FG, G is equal to a 40 millimeters. Then what else? What else? We have an R. An R is equal to 24 millimeters. 24 millimeters. Then our density, it's somewhere here. So we said it's what? It's raw. I'll just use the letter P for now. Instead of me worrying looking for some Greek letters in Python. Remember, we are just looking for some letter that can store some variable for us. So we're looking for a variable that can store some data for us. So that's our 7,850, and it's in SI units. So what I've just done there is to use everything in SI units. You can always convert to the millimeter. Since these are all in millimeters, I think it would actually be more reasonable to write the answer in millimeter to the 4. But anyway, that's what we've done for now. So for the first equation, our first equation is a straightforward equation. Our first equation is that. So the first equation is simply going to be rho multiplied by A multiplied by B multiplied by C. We multiply this by half of an A, and then we multiply this by half of a B. Rho A, B, C multiplied by half A multiplied by half B. So we're done. Okay, let's just give these names. Let's give these names so that we don't have to worry ourselves. So that is our IXY of shape number 1, isn't it? IXY of shape number 1 is equal to that value that we got. So we're happy. How about IXY of value number 2? IXY 2 is basically given by the second equation. What is the second equation? This is our second equation, PAFE. So that's our P multiplied by an A multiplied by an F multiplied by an E. I called it an ES, isn't it? So multiplied by an ES, and then after AFE, we will multiply this by half of A, isn't it? Yep. Half of A, and then we multiply it by half of E. So we called our E and ES. And we are happy. So let's check that again. PAFE multiplied by half of A, then multiplied by half of E. So we're happy. We're done. Next, we are on PABG. So that's for our IXY the third. This is equal to P multiplied by ABG. ABG multiplied by a half of A, then multiplied by a half of B. There we have it. The last term which we are going to subtract is that term here. So that's our P multiplied by half of pi r squared. So that's our pi multiplied by r. We already have r, so that's r squared. And then multiplied by a g multiplied by a half. Don't forget that this g has nothing to do with our acceleration due to gravity. So it's a parameter that I just wrote there. So half of a, and then multiplied by that bracket there. So that bracket is a b subtract 4 times r over 3 pi over 3 times pi. Done. So I think we now have Okay, this is ixy4, sorry. ixy4 is equal to that last value. So now that we are good, we can now make use of all those in this equation 1. We can now make use of all those in equation 1. So our ixy is something that we will use a lot. We can just copy that. So ixy is equal to ixy1 plus ixy2 plus ixy3 minus ixy4, isn't it? So we can then write our ixy, actually we can just paste that, and we will find our solution to be a 0 point, let's just rewrite it in this color, 0.0025, 0 and so forth. And obviously this is now in meter, sorry, this is a mass product of inertia. So we will have a kg meter to the 2. kg meter to the 2. So this means that we can actually write this as 2.50 multiplied by 10 to the minus 3 kg square meters. Our ixy is given therefore as that. You can even check its units. We have this part of the equation, kgs square meters. So that's the mass moment part. You're now writing this in terms of the mass moment. So you do the same. You use the parallel axis theorem to find your ixz and then to find your iyz. Right, that would be those would be the ones that are left. Right, so that summarizes the mass product of inertia. Mass product of inertia. Now, we are moving on to define principal axes and principal moments. Let me just take off this calculation. Now, before we actually had a definition that was highly mathematical, right? Maybe to me, but maybe to you it's very easy. So what happens is that as we will recalculate in this mass regime, we are taking almost the same setup. However, instead of us using a circle, we are actually using an ellipse. An ellipse is actually the area that will define the principal axes. Remember what we said, principal axes are just these axes at which we have maximum and minimum moments of inertia. So the ellipsoid is the area that will define that for us. So this ellipsoid is was conveniently derived by the engineers that came up with these principles. So the ellipsoid is defined in the x, y, z axis as usual. This ellipsoid, it has a center O, and it has that axis of ours, the OL axis. That OL axis has some point Q, and this point is the point whose, I think we can look at something like a locus around in all angles, whose locus creates a surface. So this locus of this Q creates the surface Q of X, Y, and Z. It is, however, conveniently located at this 1 over root of OL. So the distance OQ is actually a 1 over a root of IOL. So that your OQ squared is simply equal to 1 over IOL. So that your IOL is actually equal to 1 over OQ squared. So basically, this is the geometry that defines the derivation that is to come. So from this, you can tell that the projection of OQ on the x-axis is simply equal to, since we said this one is the lambda vector. So the projection of OQ onto the x-axis is obviously given by that dot product. So that's our OQ multiplied by the lambda x to get the projection of OQ in the x-axis. So what is OQ is just a distance from the origin to any surface point on the ellipse. The same applies for the y, and the same applies for the z. So these have been conveniently located so that we can actually replace what we had in the previous equations with our directional vectors. So you will notice that from our equation, we had an equation for the IOL. This was our equation for the IOL, and this equation reads our IOL is actually equal to all these products, right? All these products. Now we've already defined that our IOL is equal to 1 over OQ squared, where our OQ, let's say OQ multiplied by lambda x, is actually given by the distance x, isn't it? So if we make lambda x the subject, our lambda x becomes equal to an x over the OQ distance. Our lambda x becomes equal to an x over the OQ distance. Right, so if we look at lambda x squared, for example, that would be x squared over the OQ. How about lambda y squared? It will be y squared over the OQ, and so on and so forth. While on the left hand side we have IOL, which is 1 over OQ squared. Do you notice that since this lambda is squared, on the right hand side all our OQ squareds are at the what? Are at the denominator, the same as the left hand side. So on the left hand side we remain with a 1, on the right hand side we remain with terms in x, y, and z. So this is the mutation of this equation. The equation that we had before is now being written in terms of the x, the y, the z. The same applies where we have some products. On the left hand side, which is now the right hand side, where we had 1 over OQ squared, which resembles the IOL, all we have now is just a 1. So that is the equation 948. So this is still the same equation. All we are looking at it is in terms of the projections x, y, and z. Now with that equation, then we come up with a special condition which is possible, right? We come up with a special condition which is possible. Now, this special condition is the condition for the principal axis. Figure 9.31 is telling us that you can define some principal axes, but these principal axes should be located at a particular orientation. What is the orientation that we are sure will give us the principal axis? So this is just our principal axis in the x, in the y, and in the z. If you still remember from Moore's circle, we can only find our principal axis along this horizontal axis. This horizontal axis is where we have our x, ix, or our iy. However, the value of the of the product of inertia is always 0 at these locations of either the I max principal moment or the I min principal moment. So for this reason, this equation must be rewritten only in terms of the principal axis if we have a 0 mass product of inertia. So where we have a 0 mass product of inertia, which is basically where these are equal to 0, the axes are actually called the principal axis. So basically in this definition, the principal axes for mass moments and mass products are the axes at which the mass product of inertia are actually equal to 0. You will notice from what we defined some time back that lines of symmetry are where we have the 0 mass product of inertia. Look at this diagram. Look at this beautiful diagram. They have conveniently shown that you can actually position your principal axis along this axis where we have this egg shape, and it has a symmetry part of the egg shape. The same applies, there's some symmetry part of the egg shape, and the same applies for Z. So in other words, you can find your principal axes by conveniently locating them along the lines of symmetry of your body. So this equation therefore is basically defining the principal axis of the body. The IOL equation that we had earlier, right? If IOL is a principal axis, if OL is a principal axis, then our result shows that we will have it as the moment of inertia, which is equal to that sum in equation 950. So two examples of conveniently finding principal axis. If you have regularly shaped bodies, all you need is to find these planes of symmetry. If you position your axis on any of these planes of symmetry, so for example the y-axis is on that plane of symmetry, there's another plane of symmetry there, the AA prime or a plane of symmetry. Our y-axis is also conveniently located on that plane. So this actually makes your y prime axis a principal axis. Why? Because if you are to use it, right, as the axis just like that OL axis, all these products will tend to 0. So therefore you remain with the primes instead. They're actually the primes, which are the principal axis. The same applies if you have a tetrahedron. Tetrahedron, if you are to draw that axis from any apex through the center of any of the sides, you will actually get symmetry. If you rotate it, they say by what, 120 degrees, it will end up symmetric. So generally, this is our ellipsoid example of the rigid body on which you can get what? Some symmetry. So this means that the principal axis can now be defined in terms of bodies of an arbitrary shape. So this section now, it has a special ingredient. There's a special ingredient that you may have not yet covered. So that is the gradient. So you may not have covered that in calculus. So I'm not going to examine this particular part, but it's an exciting application which I believe you will need to use. Obviously next year you will have done calculus 2, so you will have this tool. But it's pretty straightforward an argument. It is just a method of finding the principal axis where the body is of an arbitrary irregular shape. So the body of arbitrary irregular shape is exemplified by this ellipsoid. So this ellipsoid, it will have some longer side, some other thinner side, and so forth. So if it is located at some origin O, and we are looking for some point P that is located a position R from the origin, and we have some normal vector through that point or at that point P, we can conveniently find these principal axes in the following manner. The calculation is based on the fact that this surface is of some function, let's call it x, y, z. So if you look at a ellipsoid, for example, let me just see if we can quickly plot it. I think we can quickly plot it. Do we have that function? I think we can. Ellipsoid, so from the previous part, we just want to plot the example of an ellipsoid. So we have what, x. We had the equation, for this mass moment. So the equation, I'll just use this equation, right? I just want to plot it so that we can at least have an appreciation of what's happening. So this is 950, isn't it? So that's the equation we want to plot. It simply has an x squared plus a y squared and a z squared. So these are in terms of lambda. Okay, so this is the part, yes. X squared plus y squared plus z squared. That's 948, yes, 948. Okay, so let's plot it. So if we have some term x squared, so this is courtesy of grapher.mathpix.com, right? So thank you very much for the programmers. So if we divide this by some parameter, let's just call it 1. Let's start with a simple case, right? Let's start with a simple case of a circle. So I'll just plot that, and I'll put this as a y, and then I'll also plot that and put this as a z. So that would be our z there. There we have it. So we should have a function now, and we can equate it to 1. So this is the ideal case of a what? Of a circle, isn't it? So a circle is just an ellipsoid whose coefficients are actually 1, 1, 1, isn't it? Or 2, 2, 2, whichever way. They're just the same. So this is our example of the circle. So to make it an ellipsoid now, to make it an ellipsoid, therefore, obviously, you'll need to stretch one of the sides. So I'll just put, let's say, a 5 for the x direction there. So what we've done is to just stretch the x direction. Now we have the ellipsoid. So the axis that we're dealing with, let's say we're looking at principal axis. We want these axes, yes, this axis that is supposed to point at us, but it will, yes, this one, yes, this one. That's a what? That's a symmetry axis, right? That's a symmetry axis. We can have another axis through there, but it will not be symmetric. We'll only find another symmetry axis on this part, and then we'll also find another one at the bottom of the ellipse there. So basically, that's our ellipse and how we can interpret it according to what we are now calculating. All right, let's just pull that ellipse away so that we can now finish off our argument. So basically, that's our ellipse, ellipsoid, and this is the function that defines the surface. So we just put a function. I think you saw that in the demonstration. So with that ellipse, the definition of this surface is given as a function. We have an equation which we can use for that. So by definition, the direction of this normal vector, do you notice that for us to have that condition of symmetry, our r vector must actually be aligned. In other words, it must be at some point P where it is in line with the normal vector. So in that case, then calculus defines now the normal vector direction as the direction at which the gradient is actually grad of f. So this is now a very special calculus function. You will use that a lot, I suppose, next year, or maybe you may have for those that are studying ahead. So this basically defines the gradient of f. So that's the gradient, grad f being equal to 2kr, where k is some constant. Why are we stating it this way? Because we said the direction of the vector is given as grad f. And then if the direction of the normal vector is given as grad f, this means that for us to align along the principal axis, we will need our r vector in line with what? With that direction grad f, which is why we actually define it as grad f is equal to 2k r. So these are specially selected constants for mathematical convenience. So that's our 9.51 equation where our r is obvious, and this is just the definition of grad f. So I know you may have not done this, but you will notice that it's simply a partial derivative. So it's just a partial derivative. Whatever is in the function f, we are just finding the derivative with respect to x, and that will be our I component. Then our j component would be the partial derivative with respect to y, and the partial derivative with respect to z of what? Of this surface function f. So this is the definition of our grad f. So if our surface function is now given by that is our surface function from our mass moments calculation. So this is still the equation. If you can tell, this is still the equation. We had it equal to what? Equal to 1, right? So we are now using this as the function that defines the entire equation. That is why we now have this equation. So basically, therefore, if you have this equation, I think you can tell that if you apply your grad f, what we are doing is we are just finding the derivative with respect to x first. So let's look at respect to x. So let's just say let me just actually write partial f partial x. Partial f partial x will have an ix multiplied by a 2x, right? Plus, with respect to x, there's no x there, so it's a 0, it's a constant. With respect to x, there's no x again. With respect to x, we have something here, so it's minus 2ixy. If we differentiate x with respect to x, then we get a 1, then we have a y. X not existing, x existing. So minus 2ixz multiplied by z, only x non-existent, so it's a 0. This equation is what we see here. So remember our condition was that this must be equal to 2kr. So let me write 2k. R in the x would be an x. So I've just equated x components. So for that reason, you should be able to see that our 2's will vanish. Our 2's will vanish. 2, sorry, let's just do that. So that's our 2 goes, 2 goes, 2 goes, 2 goes. So we now have our ix multiplied by x as the first term, our ixy multiplied by y as the second term, and it's negative. Our ixz multiplied by the z term, and that's that, so that we get the kx on the right hand side. So the system of equations 9.52 is the deal, right? This is the deal. The definition of the principal moments of inertia is just that they are the roots k. So if you have this system of equations, I guess from what we had before, we had the OQs, isn't it? We know that our OQ multiplied by lambda, for example, lambda x is equal to x. So if we now take our definition of x, it will be what? OQ multiplied by lambda x. So for the first part, this will be just OQ multiplied by, OQ multiplied by lambda x. This would be OQ multiplied by lambda y, OQ multiplied by lambda z, and then the last one would be OQ. So which means the OQs actually disappear, and then we have the lambda. So where we have an x, we have a directional lambda. So this is why we end up having a new system of equations. So this system of equations, which is 9.53, is simply a result of the previous one. So that 9.53, I guess if you subtract the right hand side, you will obviously get the k lambda x to team up with this lambda x, so that you've got an ix minus k. The same applies for the k lambda y. It teams up with the lambda y term, iy minus k, and so on and so forth. So basically, remember that the whole idea is to find the principal moments, right? So now in the end, 955 is simply a rewrite of the determinant of that matrix. So if we are to have our lambda x, lambda y, lambda z not equal to 0, then obvious the determinant of this part of the matrix is what should equal 0. So using this determinant, one can conveniently actually find the solution of the determinant to be that equation. So you can do the algebra and have lots of fun, right? So what are you doing? You're just holding, for example, ix minus k. You're holding it constant, then this multiplies that. So you've got a bracket with an iy minus k multiplying an iz minus k. Then you subtract the other ones. So what are they? It's minus iyz multiplied by another minus iyz. So that gives us your first term. So if you expand that and you rearrange, you will get equation 9.56. So using equation 9.56 and this condition that our lambda squareds all add up to 1, you can show then that this equation 9.56, the principal moments are given by the roots of the equation 9.56. So the matrix that is most important is matrix 9.55. Matrix 9.55 is the matrix that you can use to find the principal moments of a body that is irregular. So the same should be applied here, principal axis and principal moments, bodies of arbitrary shape. So in this case, obviously, you want to use this matrix. So you want to use this matrix. What do you need to find the k's, which are the solutions? You need an ix of whatever body you have. You need an iy of whatever body you have. You need an iz. Then you need an ixy, an ixz, and an iyz. If you get those 6 terms and you apply them into matrix 955, then you can find your k. So the same applies for this one. Now you would need to first find those 6 terms. So find your ix, find your iy, find your iz, find your ixy, your iyz, and your ixz. Then you plant them into that matrix and find the determinant of that matrix and equate it to 0. Basically, when you found the determinant, you will obviously have some terms in k. For example, you'd have the ix minus k as the term here, ix minus k as the term there. So it will multiply those two. If you then carry out that calculation, you will come up with a system of equations from which you can now find, for example, your k1 as one of the roots, and then you'll find a k2 as the second root, and your k3 as the third root. This actually defines your principal moment of inertia. So matrix 955 is the grail of bodies that are of arbitrary shape. Right, so basically this summarizes what we've been studying in statics. This is the end of our module, and this is the end of our calculations. My encouragement to you is that from now, besides using just the academic principle that we were playing around with all the time, focus on its application. So right now you may have some targets because you need to pass and you might be working against time. But as you can see, we can now fully describe the static condition of a body from its two-dimensional state, its three-dimensional state, its center of gravity, its equilibrium, its moments about a point, its moments about an axis, its products of inertia, its moments of inertia, its mass product of inertia, moments, mass moments of inertia, and so forth. So basically that summarizes our work for this semester. I wish you the best and all the blessings for your final tests. This is the end. Thank you very much. Have a good day.